Good morning, everyone. My name is Andreza Silva. I just finished my master's degree in agricultural engineering at the Federal University of Rural Pernambuco in Brazil. Today, I will present my research entitled Machine Learning Models for Estimating Physiological Indicators of Thermal Stress in Dorper Rams. This study was developed as part of my master's dissertation and focused on how artificial intelligence can be applied to improve animal welfare and production. Heat stress is a major challenge for sheep productions, especially in semi-arid regions. It negatively affects productivity and animal welfare. Early detection of heat stress indicators is crucial to prevent losses and ensure sustainable farming. In this context, machine learning models represent a powerful tool to predict and measure thermal stress in livestock using non-invasive techniques. Our objective was to estimate two key physiological indicators of thermal stress in Doppler rams was respiratory rate and rectal temperature. To achieve this, we use machine learning algorithms, what was random forest and support vector regression, combined with environmental data and thermal imaging, obtained through infrared thermography. The experiment was conducted in Guedes, a city in the same semi-arid region of Brazil, using Dorper Rams. We collected data on environmental conditions, thermal images of specific body regions, and physiological parameters such as respiratory rate and rectal temperature. These data were then processed and prepared for machine learning analysis. In addition to collecting environmental, thermal, and physiological data, we first applied data standardization using the z-scoring method, which allowed us to normalize the variables and make them comparable. We also perform data verification and cleaning, ensuring there were no missing values or outliers in the dataset. Next, we applied two important pre-processing steps, was correlation analysis and principal component analysis, or PCA. These techniques were used to identify redundant variables, reduce dimensionality, and highlight the predictors most strongly associated with respiratory rate and rectal temperature. For the modeling, uh, we tested two machine learning algorithms, uh, random forest and support vector regression. The dataset was divided into training and testing groups, and model performance was evaluated using statistical metrics such as the coefficient of determination, the R square, root mean square error, and mean absolute error. These metrics allowed us to measure predictive accuracy and error magnitude. This slide of the results shows the correlation between physiological and meteorological variables. Strong correlations indicated which variables were most relevant for predicting respiratory rate and rectal temperature. Here, the PCA plot presents the distribution of the variables along the first two principal components. This analysis confirmed which thermal and environmental variables contributed the most to the variability in the dataset. Together, this has results justified the selection of predictor variables that were then used in the machine learning models, ensuring that the inputs were biologically meaningful and statistically robust. For respiratory rate, rainforests clearly outperformed SBR. The rainforest model achieved an R squared of 0.858 with lower arrow values, while SPR had a lower R squared of 0.742 and higher arrows. This indicates that random forest was more reliable and estimating respiratory rate. Similar, Similarly, when estimating rectal temperature, the rainforest model once again showed superior performance with a R squared of 0.687 compared to 0.533 for SVR, although predicting rectal temperature is more challenging than respiratory rate. This is expected because RT is a thermoregulatory indicator that reflects the animal's internal physiological adjustments to maintain homeostasis. This complex internal process introduces variability that is harder for machine learning models to capture. So even so, this random forest model demonstrated better accuracy, confirming its stronger generalization ability compared to SVR. This figure shows the dispersion between actual and predictive values for both models. As you can see, rainforest predictions are closer to the real values, especially for respiratory rate. SPR present larger deviations, confirming confirming the numerical results. So, to conclude, rainforests outperform SVR in predicting both respiratory rate and rectal temperature, demonstrating stronger generalization and lower prediction errors. This confirms the viability of machine learning models as tools for monitoring thermal stress in sheep. And in the future, these models could be integrated into automated systems for real-time thermal management in livestock productions and contributing to animal welfare and productivity. So this is finishing my work. I would like to say thank you. Thank you very much, and I welcome your questions and comments. I'm free to answer any questions.